Great day, learners. Great day, learners. It's me again, Miss Bethel. So, welcome to our session about statistical experiments. Our goal for this session is to understand statistical experiments, basically talking about single factor experiment having a glimpse of CRD and RCBD. So, I'm going back to the discussion about CRD for us to picture out what's really the difference between two experimental designs. But let's define first what is statistical experiment. Talking about this, we have sets of definitions on what is statistical experiments. So here we have, it defines here that statistical experiment is actually what is controlled act through which data are collected according to some predetermined objective. It's because we consider this as a controlled act because the researcher has the ability to manipulate the data sets, to manipulate what treatments must be included, and it is highly anchored on the prescribed goal or objective of the study or experimentation. Another thing, experimental design, which gives the smallest error, is supposed to be the best design for a particular type of investigation. Of course, we allocate room for error in every experiment. Hence, this error should be very, very small so that it would not really affect our entire experiments, especially when we reach the part on computing or calculating it. Because mainly our interpretation and our discussion of the results is highly rooted on the fact that the values that we will have can be used as a prerequisite or as an entity for us to fully decide whether or not to accept, for example, our null hypothesis or reject it or otherwise accept the alternative hypothesis. Another thing, an experiment is a plan for collection and analysis of data. That's why merely we are doing experimentation because our optimum or ultimate goal rather is for us to collect data because we will be using this data for analysis, for interpretation, for creation of a specific output, or merely saying a specific interpretation or a specific conclusion. Also, the observations obtained from a carefully planned and well-designed experiment in advance only gives valid inferences. Of course, in our experiments, we are actually investing money. We are investing time, also effort. With this, we must have an accurate data. For example, you will be conducting your thesis soon. Remember, you are going to spend money for it. Thus, in data gathering, make sure that you are not doing PhD or dili ka gapang doktoro sa inyong data because it would affect your inferences. It would invalidate. That's why your thesis advisor might say, you are going to reconduct kay nagbuot-buot ka og data. And lastly, an experimental design which gives the smallest error is supposed to be the best design for a particular type of investigation. Again, nirepeat ko lang po itong part na ito. This is just the same with this part here because I would like to highlight the idea that errors are actually included, but with minimal, okay? Or with minimum interruptions for our statistical operations. So then we define what is an experimental unit or plot? So an experimental unit or plot is the smallest division of the experimental material to which we apply the treatment and can make the observation in it. Other term for this is EUs or experimental unit, shortened EUs. For example, your experimental unit is a plant, so a corn plant, or your experimental units are animals. So each sheep or each lamb or each chicken or each horse or swine or pig is considered as an experimental unit. Or talking about human beings, then each person is considered an experimental unit. How about the treatments? So the treatments, talking about this, are characteristics which are to be investigated through an experiment. And it serves as the objects of comparison in an experiment. So we have this example here. So we have examples, effects of different fertilizers. So for example, you have four fertilizer, four kinds. So it could be organic, it could be muriate of potash, it could be a complete fertilizer, or it could be ammonium sulfate, or it could be different levels of fertilizer. Like you are applying chicken dung, but with different levels. Probably you apply half kilo, that's level 1. Level 2 would be 600 grams. Level 3 would be 700 grams. Level 8 would be 800 grams. Level 8 rather, level 3. Okay, so those are examples of treatments. Or it could be the yield of different varieties of crop could be considered as a treatment. Or disease resistance of different cultivators. So things like that are considered as treatments. Okay, so how about statistical principles of design? Let's talk about this one. So an experiment is actually the act of conducting a controlled test or experimentation. Again, I've mentioned earlier that it is a controlled test because the researcher has the ability to manipulate the data, or not the data rather, to manipulate the experimental units, to manipulate the treatments, okay, according to a predetermined objectives or goals. And the word controlled means most, if not all, of the conditions that happened or were used in the experiment are known or regulated. For example, you are going to conduct the experiment inside a greenhouse. So inside a greenhouse, the temperature is controlled, the humidity is controlled, okay? The penetrance of light is controlled. And the word design may mean arrangement, taking into consideration proper design. Okay, it's important because we want to establish or create or find the two results without any doubt in mind. Okay, because rest assured that you use the proper arrangement. So you should not be doubting your inference or your results or conclusion. Another thing, experimental design may refer to the arrangement of experimental units used to control experimental error and at the same time accommodate the treatment design in an experiment. So this includes the plan and actual procedure of layouting the experiment. That's why when we talk about CRD or RCBD or Latin square design, each of those mentioned experimental designs has its specific layout or randomization scheme. And EU, as I've mentioned earlier, refers to the unit of experimental material to which a specific treatment could be applied. This could be a single leaf, it could be an entire plant, or it could be per pot basis, or per plant basis, or it could be a single pen, not the ball pen, but single pen of animals, kunwari, to which a treatment is applied in a single replicate. And treatment is the set of circumstances created for the experiment in response to research hypothesis. So it could be a kind, it could be a dosage, it could be a level, or it could be a method being tested in an experiment. For example, treatment, the same with your exam, right? For the midterm, control over the supplements and those people or patients which didn't have control over the succulents because the succulent is being taken care of by the staff. And another thing, experimental error describes the variation or the differences among identically and independently treated experimental units, meaning they are just treated using the same treatments, but treated individually, okay, or independently. But what is treated or used as treatment for the single, okay, a single experimental unit is just the same with another separate experimental unit. Or otherwise saying the difference between experimental units treated alike, okay? Or the variation between experimental units. So if our experimental unit is a plant, so the variation between two corn plants or the leaf sheets of two corn plants treated alike, okay? Another thing. Now, let me ask you, what are the sources of experimental error? So we have here the natural variation among experimental units. So when we talk about natural variation, like the researcher has limited control over this. When we talk about natural variation, it could be due to the genetic, okay, inherent capacity of the plant or the animals, or other features that are really innate in that specific experimental unit. Second one is variability in the measurement of the response. Third one is inability to reproduce the treatment conditions exactly from one unit to another. So for example, if there is a gradient, talking about fertilizer gradient, or it could be the source of water. The source of water is just at one side when we talk about experimentation for flooding, or it could be talking about experimentation in corn exposed to drought resistance. So there's water involved. So what would be the amount of water that is lacking or missing in that area, talking about drought or talking about flooding? The source of water for the moment you will impose your flooding as the treatment, or it could be the occurrence of pests in an area, or the occurrence of diseases in an area. And then fourth one is interaction of the treatment imposed and the experimental units used in the study. Fifth one is the extraneous factors that influence the measured characteristics or other factors. So there are also three important principles inherent in all experimental designs or innate, okay, sa tanan or sa lahat ng experimental designs. Be it CRD, be it LSD, or the Latin square to be more specific, or be it RCBD. So first one is replication. The number of times a treatment is repeated. That's why you would have T1R1, T1R2, T1R3. So, or T2R1, R2, R3, or it depends up to how many replications is given. So this replication provides an estimate of the experimental error and a more precise measure of treatment effects. And the second one, the number of replications highly depend on the magnitude of the difference you wish to detect and the variability of the data. So if you wanted to really detect the differences of a specific treatment or the differences of a specific variety or the variability of the data that you obtain, then you should replicate, or there's really a need for us to replicate our study. And the second one is randomization. So this is highly done in all experimental designs. So the assignment of treatments to experimental units so that, quote unquote, all treatments considered have an equal chance of receiving a treatment. So it provides an unbiased estimates of treatment means and experimental error. And lastly, the local control. It describes the action the researcher employs to reduce or control experimental error and, of course, increase the accuracy of the observation. Again, let me ask you, what are the three important principles inherent in all across, okay, in all experimental designs? First, we have replication. There's a need for us to replicate, to do randomization, and to have local control. So we also have points of control in our experiments. First, we have the technique. So talking about the technique, we should have accurate or correct measurement. Preparation of the media, for example, if you use soil, then make sure that the soil, the source of soil is the same, okay, for all the pots, if it is a pot experiment, or making sure that the soil is free of any other kind of diseases that might affect your experimental unit, or pipetting of solutions if you are doing, or if you are involved in a study which really entails the use of some chemicals or some reagents. Then we also need to calibrate the instruments that we're going to use. For example, you are going to determine the weight of the leaves, or it could be we are going to determine the weight of the kernels, or the weight of the swine, or the weight of the sheep. We must ensure that our timbangan, okay, is actually well calibrated. Kay basid nagbaon ang ato ang timbangan, and what happened? First nimo nga gi-measure is ang baboy, titimbang nimo, okay, sakto. Pagka-second nimo nga timbang sa imong baboy, what happened is that naanay difference nga 1 gram. So it matters. Okay, it would be added to the experimental error. So there's really a need for us to calibrate our instruments. And of course, uniform application of treatments. That's why in doing your thesis, you should really be honest. Okay? You should be honest. You should be committed in the conduct of your thesis. Because once, for example, supposedly you are going to apply the foliar fertilizer early in the morning. But then, what happened was matagal kang gumising. So ano yung nangyari? Late ka nang gumising. Instead of applying the foliar fertilizer at 6 a.m., you applied it at around 11 a.m. So it matters because the absorption of the organic foliar fertilizer is different because there is already an intense solar radiation. So it would affect as well the performance and yield of your crop of interest or your experimental unit. So the technique is very important. And selection of experimental units. There should be balance between the range of conditions and uniformity of units. For example, if you are going to study chicken, then make sure that the chicks that you are going to use are of the same age, okay? Or if possible, of the same mother hen. Or if lisodjud siya, of the same company, if you buy chicks from San Miguel kunwari, or if you buy chicks from a local poultry, okay? Or it could be choosing plants. Make sure that the plants that you use to be part of your experimental units are, of course, this is free from insects, okay? Free from any pests. Because out of 10, kunwari, kung may isa dyan na napili mo, tapos sakitin yung halaman na yun, it would matter. Probably it would die. Or probably its photosynthetic efficiency is not that good. So it affects your conclusion, especially when you talk about the dry matter yield. Of course, yung dry matter yield ng halaman na yun, medyo mababa talaga kasi CK naman yung halaman. And the third one is blocking. Blocking is very important, especially when we talk about RCBD. So experimental units are grouped into blocks to minimize variation within block. For example, later on, we will discuss this the moment we will reach RCBD. So because there are differences, talking about fertilizer gradient, there is a difference when we talk about source of light or source of water, or there is a difference when we talk about if that whether that area is highly or densely populated with weeds or densely populated with insect pests and other diseases. Fourth one is the choice of experimental design. So if we're going to choose RCBD, what would be the advantage and disadvantages? How about Latin square design or CRD? So we need to choose the simplest design which would tailor or suit our objectives of the experiment. If you do not need blocking, then there's no need for you to use RCBD. You could use simple CRD. And fifth one is the measurement of covariate techniques. So these are the variables related to the response variable of interest. This is actually used as a statistical control on experimental error variance by, of course, the analysis of covariance procedure. But you would be discussing this more in your lecture. 6.1, proper plot technique. So we are going to orient the plots parallel to the gradient. So if this is the gradient going to, this is going to the left, of course, your plots should also be oriented parallel to the gradient. When we say parallel, of the same direction, no? So this is parallel, this is another parallel. So same direction po yung dalawa. Seventh one is data analysis. So use of data transformation for data with high coefficient of variation because there is only an allowed CV. That's why in your thesis po, so if your CV is very, very high, your teacher might ask you to transform your data. Or worse comes to worse, no? Pwede niyang ipareconduct kayo. Depende naman din kung ano yung experimental units nyo at saka ano yung goals ng study nyo. Kasi meron lang po accepted na coefficient of variation.
Now, when can we say that we actually choose the most appropriate experimental design? So here are the criteria. First is when we already attained maximum information, precision, and accuracy in the results, along with the use or most efficient use of existing resources. Or other way of saying this in relation to what Jegoro Kano, the founder of judo, told us, no? Or is common for saying this. Maximum efficiency with minimum effort. Diba nga in judo, you're not going to fight strength with another strength, but you are going to use the opponent's momentum to unbalance him or her. So if your opponent would push you, you will pull him or her. And if he or she will pull you, you will push him or her. Again, in statistics, we require maximum efficiency, maximum precision, maximum accuracy, with maximum as well, maximization of resources or most efficient use of resources. Or like we're required to use less but have good results, things like that. So for ANOVA or analysis of variance, it is actually the process of subdividing the total variability or total differences of the experimental observations into portions attributable to known sources of variation. So this is one of the assumptions, additive effects. So we are trying to consider linear additive model, multiplicative model with block effect as to no interaction between blocks and treatments. So we have this different formulas here or model. Okay. So we have different models for linear, for multiplicative, and with block effect. Or basically, we're using this for RCBD. I am just showing you these things because you will be in probably in the future you will be encountering this, and then you will tell that your statistics professor did not told you about these things, but these things shall be discussed in your lecture presentations, no? So showing to you that there are actually models of assumption of the analysis of variance. Also, we expect normal distribution. We consider independence of errors. This is actually assured by randomization. Diba? In all experimental designs, we do randomization. So with this equation, we must know that errors are distributed normally and independently with mean 0, this one, and variance. This is actually the variance. And homogeneity of the variance. So variance of errors, or this one, is considered the same for all the treatments. So how about the interpretation of the results of ANOVA? Actually, you are familiar with this. HO, or the null hypothesis, is rejected. So considering it's highly significant with 2 asterisks, treatment difference if the computed F is greater than the tabulated F at 1% or 99% confidence level. Chances are less than 1 in 100 that all observed differences among treatment means could be due to the chance. HO is rejected, so significant treatment difference if the computed F value is greater than the tabulated F value at 5% or 95% confidence interval, but less than the tabulated value at 1% or 99% confidence interval. HO is not rejected, therefore it is accepted when the result says there is non-significant difference of the treatment mean. So basically, if the computed F is less than 5% tabulated F value. Again, when can we see that we must reject the hypothesis, the null, if it is highly significant or significant? Highly significant when ang computed F na to is greater than the F value at 1% tabulated. Okay? Also, when it is significant, kano sa siya significant? Kung mas dako siya sa 5%, pero mas gamay siya sa 1%. Again, mas dako sa 5%, pero mas gamay sa 1%, we're going to consider that the treatment means are significant. Therefore, reject the null hypothesis. Kanus-an na to i-accept si null hypothesis? Kung non-significant ang result. So, kung ang atuang computed F mas gamay sa tabulated F at 5%. I hope klaro. Bisaya po siya, para mas klaro. And what is the meaning if NS or non-significant? But pasabot ba nag-fail ta sa ato experiment? Of course not. It is indicating the failure of the experiment to detect any difference among treatments. So for example, di ba na-iyon ko ganiya, failure ba imuhang entire experiment? Of course not. Wala lang na-detect sa experiment nga na ay differences sa treatment means. Does not prove that all treatments are the same. Okay? Dili ubot pasabot nga pareha gyud ang treatments isa-isa, they are just the same, no? It's not the right meaning when we talk about NS. So failure to detect treatment difference could be the result of a very small or nil treatment difference, a very large experimental error, or both. But if the experimental error is not large, and then the case is this, na ay ang imuhang feeds, nagbuhat kag own feeds nimo. Imo siyang gi-compare sa mga currently available feeds nga naa sa market. And then, ang result, NS. Pero gi-consider nimo nga gamay ang experimental error, sakto imong mga data sets, sakto imong imong technique, imong blocking, imong randomization, imong plotting techniques. All the other factors were done appropriately and precisely, accurately. But an NS pa ng result. Will you be happy? Yes, you should be happy. Because considering that all the other factors are done appropriately, accurately, and precisely, tapos NS pagyapon ang result, dili dako kay experimental error, acceptable ang experimental error, but pasabot, kung if you're going to measure the effectivity of your created feed staff ratio, tapos the same lang NS siya compared sa mga available sa market, nga mas barato ang imuhang feed formulation or ration, mas barato imong mga raw materials, pero parehas na siya effectivity sa mga available sa market. So, di na di ka kailangan magpalit adto. Kaya pwede ikaw na yung magbuhat kay NS imong result. Diba? That's one good thing. Now, it doesn't mean nga NS imong result, tapos, sayop tanan imong experiment. NS ang result, imo gyud ang gihatag sa imuha when you did your calculation and other statistical procedures. Only if you did the experimentation properly and accurately, considering that experimental error is not large enough. Okay? Another thing, when F test is non-significant, the researcher should examine the size of the experimental error and the numerical difference among the treatment means. If both large, the trial may be repeated. Kana siya. They say, good kaayo, no, there's something wrong with your data gathering, or there could be something wrong with other circumstances involved in the study. And efforts made to reduce experimental error. If both values are small, the difference among treatments is probably too small to be of economic value and no additional trial is needed. So this is what I am telling you. Na parehadeg effectivity ang imong gibuhat nga feed formulation or feed staff ratio compared sa mga baligya sa merkado. So malipay ka dapat. Okay? So this is case number 2. This case here. So how about the CV? Unsa man pwedeng CV class? You kept on encountering the term coefficient of variation. So the coefficient of variation would indicate the degree of precision with which the treatments are compared. Mo na siya sa iyong thesis pohon, tan-aw na sa iyong mga professors or sa iyong mga advisor kung taas ba kayo ang CV or kung gamay ba kayo ang CV or within the range lang ang inyong CV. Because again, what is a CV? An index of reliability of the experiment. And it is dependent on the type of experiment, the crop grown, and the character measured or responses measured in the experimentation. For example, for data on rice yield, the acceptable CV is 6 to 8% for variety trials, 10 to 12% for fertilizer trials, and 3 to 15% for insecticide and herbicide trials. So for example, you're doing your thesis, so you're assessing the performance of regional rice varieties grown in Bukidnon. So planted siya in Muswan, under Muswan condition. So naakay 30 ka varieties sa rice. Asa di sa ilaha ang pinaka-persistent or pinaka-high yielding. Tapos imong CB 20%. So variety trials, so mag-wonder yung professor, ano is 20% pa niya? Ang acceptable CV is 6 to 8%. So the professor will tell you, okay, please give me your raw data. I would like to check atong nag-data gathering ka. That's why also, when you do your thesis, it's good to have a record book. In the record book, dira nimo isulat tanan nimo nga data gathered. O mas importante nga imong gamiton pagsulat is lapis. Kaya kung lapis, kung mabasa sa ulan, nag-data gathering ka, nabasa sa ulan, dili siya mapangit ang ink, naaragyapon siya kay dili man siya mag-blot ang ink. So 10 to 12% again for fertilizer trials and 8 to 15 for insecticide and herbicide trials. I repeated it, no? So the CV for other plant characters usually differs from that of yield. For example, where CV for rice yield is 10%, tiller numbers Okay? Or tailoring capacity, 20%, pwede nga CV. Kung plant height, ang CV po is only 3%. So, it differs, no? It differs rather kung depende po sa imuhang gina-measure nga character. And let's proceed now to completely randomized design or our CRD. Let's talk about the advantages and disadvantages of completely randomized design. First is it's easy to implement, especially into assigning treatments no, to HTUs or so-called randomization. You will not have a problem with this. You just need to assign all the treatments to all the experimental units. Second one is making sure that it's assigned between replications. Second is simple calculation of the analysis variance. So for your ANOVA table, it's very easy to memorize, to be familiar with the treatments, the total, and the error. Third one is completely flexible for number of reps or treatments. Also, missing observation is not a problem. So, kunwari, if you are studying growth performance of swine as affected by a specific feedstuff, then swines now are very expensive or costly. Then, what if may manamatay? No? Kasi nagkasakit. Kunwari na ASF yung isa lang. Pwede ba yun isa lang? Pwedeng lahat na ASF or like isa or dalawa lang yung ASF. Tapos yung isa, yung iba na-save, naka-recover sila. So you will not have a problem when we talk about CRD kasi pwede namang mag-calculate ng ANOVA using an equal replication. Fifth one is maximum error DFN design. So disadvantages naman, it requires uniform or homogeneous experimental units. So if you're going to conduct a thesis in a field condition, do not use CRD. But if you're going to use a greenhouse, no, you just use spot experiment inside that greenhouse or inside a laboratory. Yeah, CRD is good. Second one is all non-treatment variation is considered as error because you have no other source of variation but your treatment tapos error DF tapos total lang. So, allocate mo talaga siya na hindi to dahil sa treatment o di, of course, error to. Ganun. Okay? Unlike RCBD, kung hindi dahil sa treatment, pwede namang dahil sa blocking. Pwede namang dahil sa replication. Okay? Pero, all non-treatment variation in CRD is considered as error. So, the higher the error DF, the better is your estimate of the error. And F value is computed only when the error DF is large enough for a reliable estimate of the error variance. So, dapat 6 or more lang. Kung hindi siya 6 or more, yung error DF, then it's not good. O hindi siya po pwede for CRD. Parang ma-invalidate lang din yung ANOVA mo. Okay, let me repeat. F value is computed only when the error DF is large enough. It should be 6 or more than that. So here's the model for CRD. So importante talaga sa class na may mga models. Okay? So Xij is the overall population mean plus the effect of the I treatment plus the residual or error effect of the J treatment or of the I treatment. Let me repeat again kasi J treatment yung nagamit ko kaninang word. Residual or error effect of the J measurement of the I treatment. And division of the IJ observation from the I treatment mean naman yung ating AIJ. Okay? So, just remember the model. We have, okay, for easier, no? Para matandaan natin kahit nasabihin nyo na lang na M plus TI plus AIG. Okay? Pero, of course, you should know what's the meaning of that M na sinasabi mo or mu or the overall population mean. Tapos yung effect ng I treatment, NID stands for normally independently distributed, considering the variance. Okay? And here's the randomization for our CRD. So, for CRD po, again, yung sinasabi ko kanina, kunwari, meron tayong CRD with 4 treatments, treatments A, B, C, at saka D. Tapos alam mong meron kang 16, no? 4 treatments, tapos 4 reps. So, 16. So, i-assign mo lang siya sa buong experimental unit. Kahit na magkakatabi pa sila, or kahit na hindi sila magkakatabi, or kahit sa isang, kasi wala ka namang blocking, kahit dito, puro A pa to, pagka yun talagang result ng randomization mo, or dito B, B, C, C, okay lang yun, kasi CRD naman yung ating ginagamit. Hindi siya ganong stricto when we talk about randomization. Okay? So, I wanted you also to, of course, study your learning module, the ones I've given you as soft copy, when we talk about CRD na randomization. Kaya we have here, again, this is for 4 treatments for application. So, simply assigning, no, the different treatments to the 16 experimental units. I hope that's clear. So, for ANOVA naman, importante po ang ANOVA na ma-memorize natin. First po na column, si V, tapos DF, tapos sum of squares, mean squares, FC, F-tab at 5%, F-tab at 0.1% or 1%. Okay? So, TET din. So, for ANOVA ng CRD, TET lang. So, ano yung TET na yun? Treatment error total. Para makuha natin yung DF, minus 1. For the treatment naman, TRDF, T minus 1. For the error, T times R minus 1. Or treatment multiplied to replication minus 1. For the total naman, replication times treatment minus 1. For the TRSS, ESS, TSS, okay, this is the treatment SS or sum of square, error sum of square, and total sum of square. MSTR stands for mean square of the treatment. MSE is mean square of the error. To compute for the computed, ano daw, to have our computed F value, we multiply the mean square of the treatment to the mean square of the error, or MSTR over MSE. So, class, madali lang itong lahat. Kasi pagka alam mo yung sunod-sunod, no? TET, tapos alam mo to kung paano ito i-solve. Ito din, TRSS, ESS, TSS, MSTR, MSE, makukuha mo yung computed F natin. So, for our equations naman, pakatandaan, unang-una, kailangan natin kunin yung summation of x or summation ng mga values. Alam din dapat natin ano yung sum of squares at square of a sum. So, to compute for the CF or the correction factor, this one, so we get the square of the sum over the n. N po, yun po yung total number of observations. For the total sum of squares, we just subtract the correction factor from the sum of squares. Take note po, pagka mali na po yung ating, okay, summation of x, mali yung sagot natin sa square of a sum, at saka mali din yung sagot natin sa total number of observation. Mali na rin yung CF, so mali na din ang lahat ng ito. Kasi nag-ugat po siya sa CF. Nag-ugat din po yung CF sa summation of x. Compute for our treatment sum of squares, we just simply divide the sum of squares, the treatment means, over the replication minus the correction factor. So that's for the treatment SS. Again po, sum of squares of the treatment means. Tapos yung ESS naman, yung error sum of squares natin, it's simply total SS minus treatment SSS. SSS. Ano yun? So, just kidding. So, treatment SS lang po. So, bali po, pagka nakuha natin yung TSS natin, dapat tama po yung sagot. Tapos, pagka nakuha natin yung tamang sagot sa ating treatment SS, tama din, of course, ang ating error SS. Tapos, hindi po siya SSS ha, iba po yun. Agency po yun. Mean square of the treatments naman, i-divide lang po ang ating treatment SS sa ating treatment TF. So, makikita po natin ito sa ating ANOVA table. For the mean square of the error, we just divide the error is at SS, kung hindi SSS, SS naman. Okay, we just simply divide the error SS to the error DF. And of course, we need these two values to compute for our F. Okay, so MSTR over MSE is our computed F value. Okay, docs? So now let's have our sample problem. Suppose we wish to test 3 different hormones, each at a single dose to determine their effects on the weight gaining ability of the sheeps. Including the control, there are 4 treatments, assuming the experimental unit to be a single sheep, and if 4 sheeps will be assigned to each treatment, there will be 16 sheeps. So, weight gain of sheeps grouped by treatment, so pound per animal per 100 days. Numbers in parentheses are ear tag numbers of the 16 sheeps assigned to the trial and randomly selected to receive the indicated treatment. So, ang ating T1R1 po ay yung sheep number 14, T1R2, sheep 13. Ito po yung product ng ating randomization scheme at saka layout. Treatment 1R3 ay yung sheep 9. Yung treatment 1R4 rather is our sheep number 8. Tapos 12, 11, 6, and 5 are part of treatment 2. Sheeps 2, 7, 1, and 15 are part of treatment 3. Tapos T4R1, sheep 3, T4R2, sheep 4, T4R3 is sheep number 10, and T4R4 is sheep number 16. With their corresponding weight gain in pounds. So, 47 pounds po yung na-gain ni sheep number 14 nung trinit siya ng treatment 1. Okay? So, yun po yung ating ibig sabihin. So, ang unang gagawin po natin is i-total po natin yung lahat na nasa treatment 1, yung lahat ng replication. So, 47 plus 52 plus 62 plus 51 is 212. So, gawin din po natin yun sa treatment 2, sa lahat po ng replications, rep 1, rep 2, rep 3, rep 4. So, 50 plus 54 plus 67 plus 57, 228. Sa treatment 3 naman po, replications 1 up to 4, 57 plus 53 plus 69 plus 57 is 236. Lastly po, sa ating last na treatment 4R1, 54, plus treatment 4R2, 65, plus treatment 4R3, 74, plus treatment 4R4, 59. The total is 252. Ngayon po, kunin natin yung mean per treatment. So, ilang replications ba? 4. 1, 2, 3, 4. So, i-divide po natin yung 212 sa 4. The result is 53. I-divide din po natin yung 228 sa 4. Bakit po 4 ulit? Kasi meron po tayong 4 replications sa treatment 2. The answer is 57. The same is true with treatment 3 kasi po 4 din po yung ating replication sa treatment 3. So, i-divide po natin yung 236 sa 4. Ang answer po ay 59. I-divide din po natin yung 252 sa 4. The answer din po is 63. Now, if we're going to get the sum of all the totals or summation ng lahat ng values na to, the answer is 928. Pag kukunin din natin yung mean po nito, the answer is 58. So this one, the mean of this, if we're going to add this and divide this to 4, the answer is 58. If we're going to divide this number, saan po ba natin i-divide yung 928? Sige nga po, saan natin i-divide yung 928? Of course, i-divide po natin yung 9 to 8 sa ating total experimental units. Ano po ba yung total experimental units natin? 16. Saan po ba ulit nakuha yung 16? Kasi po meron tayong 4 na treatments tapos 4 na replication. So 4 times 4 is equals to 16. Saan po ba yung 16 na yun? Ito po, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yun na po. Okay. Medyo napabilis po yung counting ko. Okay? Medyo nahuli po yung aking kamay. Pero 16 po ang lahat ng ito. Hanapin po natin yung number 1. at saka yung number 16, ito po. Okay, so dapat 16 na experimental units. We are just going to divide 928 to 16. The answer is 58. The next step for us is to get our DF. Again, to compute for the treatment DF, simply subtract 1 from the treatment. Ilan po ba yung treatment natin? Okay? Balikan natin. 1, 2, 3, 4. So, 4 minus 1 is equals to 3. Yung error naman po, T times R minus 1. Ano po ba yung T natin? Or ulit. Ano po ba yung replications natin? 4 ulit. Kasi, 1, 2, 3, 4. So, sabi din sa ating problem, kanina, including the control, there are 4 treatments. Assuming the experimental unit to be a single ship, and if 4 ships will be assigned to each treatment. Ito po yun. 4 ships daw. Yun po yung ating replication. So, 4 minus 1 is 3 times 4 is 12. For the total naman na DF, we just multiply replication times treatment. So, 4 times 4 is 16 minus 1 is equals to 15. So, tapos na po tayong kunin lahat ng ating mga DFs. So, ngayon po, kasi alam na natin yung summation of x, alam na din po natin ang ating mean, we can compute for the CF. G squared po. Ano po ba yung G squared? G squared is just the same with this one. Okay? Summation of x, bali G squared lang po, or in some literatures, ang ginamit po nila ay GT. G kasi po grand total, or GT kasi po grand total. So we just need to square the grand total. So 928 squared divided by RT. So 4 yung replication, 4 din po yung ating 4 din po yung ating replication tsaka treatment. So the answer is 53,828. Or rather 824. So you could recompute this up, Tapos yung total SS naman natin is sum of squares minus CF. So this is squaring all of these values. Tapos, ito pong 47 squared, 52 squared, 62 squared, 51 squared, 50 squared, 54 squared, 57 squared, 57 squared, hanggang umabot tayo sa 59 squared. Lahat po ng values na ito, i-square natin isa-isa. Tapos, i-add po natin silang lahat. Ang total po nun ay 54,678. I-subtract po natin yung ating correction factor sa value na ito to come up with 854. For our treatment SS naman, ano yung ating i-square isa-isa at saka natin i-add? Ito po. Ito po yung ating treatment. So, 212 squared plus 228 squared plus 232 squared plus 252 squared minus the correction factor. Tama nga. Sorry po. So, minus the correction factor. So, itatry po natin ha. So, 212 squared plus 228 squared plus 236 squared plus 252 squared. The answer is 216,128. I-divide po muna pala natin siya ng 4. So the answer is 54,032. I-subtract po natin yung ating correction factor, which is 53,824. So the answer is 208. Verify nyo din po sa inyong calculator. Okay po, sana po ay meron kayong calculator ngayon. Hindi po tayo parang nanonood lang ng vlog, kundi nag-aaral din po tayo habang nanonood. For the error SS naman, pagka nakuha na natin yung total SS at saka yung treatment SS, very easy na. It's TSS minus treatment SS. So 854 minus 208, the answer is 646. So we're almost done actually. So ilagay na natin yung values kanina, di ba? Nakuha natin kanina, treatment SS 208, total SS 854, error SS 646. I-plug in na po natin yung ating values ng mga sum squares dito sa ating ANOVA table. Tapos na din po kasi nating i-compute yung ating mga DF. Ngayon naman, kukunin natin yung MSTR. Para po makuha yung MSTR, i-divide lang po natin ang ating TRSS sa TRDF. So, bali po, pagka nakuha na natin yung part na ito, madali na pong kunin ang lahat. Okay? Kasi 208 divided by 3, the answer is 69.33. Para naman po kunin ang ating MSE, i-divide lang po natin ang ating ESS or error SS sa ating error DF. So 646 divided by 12, it's 53.83. Paano naman natin makukuha ang ating FC or F computed? Okay po, para makuha po natin ang ating F computed, i-divide po natin ang ating MSTR over error or MSE or the mean square of the error, error mean squared. So try nyo po. 69.33 divided by 53.83. The answer is 128.79. So calculating or rounding this off to 2 decimal places, it's only 1.29. Tapos po, paano natin masasabi na NS siya? Ito po pala. So, tignan po natin sa ating F tabulated. Okay? Titignan po natin sa F tabulated natin. So, ito po ang ating F tabulated. Okay? Pakatandaan po natin na ang ating pong gagamitin ay ang ating treatment DF at saka error DF. Okay? So, bali po, kaso di ko po siya nasulat dito. Dito lang po ako nakafocus. Bali po, ang gagawin natin, itong part na ito po ang ating treatment DF, tapos ito po ang ating error DF. So, kaya po, we came up with ating 3.49 sa ating 5% at saka 5.95 sa ating 1%. Ngayon, pwede na tayong mag-create ng ating conclusion. Sabi dito NS. Bakit NS? Kasi po, mas maliit ang ating F computed kaysa ating F tabulated. Right? At 5%. Diba sabi kanina, kung mas maliit ang ating computed F kaysa ating F tabulated at 5%, automatically NS. Ibig sabihin, there is no significant difference on the effects of the 4 treatments on the weight gain of the 16 sheets. So, pare-pareho lang po almost yung differences po, kahit po iba-iba po yung treatment. Okay? So, there's no significant difference on the effects of the 4 treatments on the weight gain of the sheets. Now, titignan naman po natin ang ating CV. So, to compute for the CV, it's just square root of MSE over the mean times 100. Ano po ba yung ating mean kanina? 58 po. Ano po ba yung ating MSE? 53.83. So, square root of 53.83 divided by 58 times 100, it's 13.34%. So, yun po, ganun lang po kadali ang ating CRD. ANOVA ng CRD with equal replication. Paano naman po pagka unequal replication? Kunwari, namatay yung shift natin sa replication 3 ng treatment 4 at saka namatay or nawala or gikawat yung shift natin sa treatment 2 R4. So, ito naman po yung ating scenario. Completely randomized design with unequal replication. So, weight gains of sheep's group by treatments found per animal or per sheep for 100 days. Number in parentheses are ear tag numbers of the 16 sheep assigned to the trial and randomly selected to receive the indicated treatment. Kaso nga po, namatay po yung ating sheep number. Tignan po natin dito ulit. Sheep number 5 at saka sheep number 10. Tama diba? Namatay po sila. So, assuming na namatay or gikawat sila no, or nawala sila. The lost sheep, literally. Okay? So, same lang din po yung ating ginamit na data. So, kukunin po natin yung total. Same lang po yung total ng treatment 1 kasi kompleto naman po yung ating sheeps. Treatment 3 din po, same lang din po yung total kasi kompleto yung ating sheeps. Kaso sa treatment 2 po, namatay o nawala po yung sheep natin na pang 4th replication. So, we add 50 plus 54 plus 67, it's 171. Tapos, 54 plus 65 plus 59, it's 178. So, we are going to divide 171 into 3 or 4? Into 3. Because we are only having 3 values, no? So, 171 divided by 3 is 57. Dito naman, sa treatment 4, into 3 din. Kasi po namatay or nawala po yung ating sheep. 178 divided by 3, it's 59.53. Kung kukunin po natin lahat po ng values, i-add po natin ito, ang total po ay 797. Ito po, pag i-add din po natin lahat ng treatment means 797 po. Kung i-divide naman natin yung 797 into how many EUs or experimental units? 16 pa rin ba? Of course, hindi na po siya 16. Kasi po, namatay po yung dalawa. Wala naman pong shift dito na pang-apat sa second treatment. Wala din pong pangatlong shift dun sa ating fourth treatment. So, i-divide po natin ang 797 into 4. The answer is 56.93. If we're going to get din naman po the mean of this, it's actually, if we're going to round this is 57. So, 53, saglit lang po kuha tayo ng calculator. 53 plus 57 plus 59 plus 59.33 divided by 4, it's 57.08. So, 57 lang din po. So, if we're going to round this off po, 57 lang din. Pero, para po, mas accurate yung ating answer, i-divide na lang po natin ang ating grand total kung ilang i-use. So, 797 divided by 14, the answer is 56.9285. Kaya po naging 56.93. So, ganun din po yung ating proseso. Kukunin po natin yung ating CF. Again po, para kunin yung ating CF, you're going to square the GT or grand total, or you just simply square the, anong isa-square natin? Ang ating summation of x. So, 797 squared divided by, ilan po ba yung ating n ngayon? 14 na lang po kasi po namatay yung dalawa. 16 minus 2 is 14. So, the answer is 45,372.07. Again po, pagka po gagamitin natin 4 decimal places po pwede naman pong 2 pero stick po tayo sa 4. Pwede, ang i-write natin dito ay 0.07 pero yung gamitin natin sa calculation, pwede namang 0.07. Pero as much as possible po, pwede itong 4 decimal places. So, for the total SS, we just simply get the what? This is actually the sum of squares minus CF. So, square po natin isa-isa yung 47, 52, 62, 51, 50, 54, 67. Square po natin to isa-isa. I-add po natin. The answer is 45,953 minus the CF, which is 45,372.07. The answer is 580.93. So, 4 minus 1 is equals to 3. Yung error naman po ay n minus t. So, n po natin ay 14 minus treatment, which is 4. So, 14 minus 4 is 10. Yung total natin ay n minus 1. Kaya 14 minus 1, that's 13. So, ang ating pong SS, saan po natin nakuha tong values na to? Galing lang po sa ating previous calculations. Plinag-in lang po natin yung ating mga values. To compute po for our MSTR, so 96.26, which is the TRSS divided by 3 is 32.09. 484.67 divided by 10 is 48.47. To compute for our FC, or to compute for our F rather, so computed F, 32.09 divided by 48.47, it's 0.64. To get this one, the same concept or the same principle kung nung tinuro ko kanina, tignan natin kung saan yung ating treatment TF at saka our TF. So, then po nagtatapos ang ating discussion for CRD. Review lang po ito para mas maintindihan natin kung ano ba yung kaibahan ng CRD sa RCBD. So, watch out for our next learning video. Thank you and God bless us all.